There's been a bit of talk, a bit of chat about this. My computer's going too slow. Do I need an SSD? How do I make my computer go quicker? And I've had this same conversation with a number of people about disk speeds. So I thought what I'd do is I'd go through basically all of it. I'll take a wee minute or two to do, but it's probably worth, hopefully by the end of this, you'll know a wee bit more about disk speeds and some of the options available than you do at the minute. And if one or two people are a wee bit more enlightened at the end of it, that'll make me feel really, really good. First of all, if you've got a computer program, the disk speed doesn't make the computer program run any more quickly or more slowly. That's dictated by the processor speed, the memory speed, and if you've got a GPU, by that. However, there's a big exception here, and that is to do with the fact that if your program has got Windows plus the program, or Linux plus the program, or whatever running, and it takes more memory than you have on the board, and if you've got 4 gigabytes of RAM, then I'm looking at you. And what happens then is that the operating system has to shuffle stuff from the disk to the memory and from the memory to the disk constantly. If you think about it, when you put one window in front of another window, the stuff that was in the window at the back is no longer needed. And so the operating system says, right, I can take that and put that on the disk. And then when you press that window and bring that window to the front again, it has to take the stuff in the other window, put that in the disk, and take the stuff that was on the disk and bring that to the front window. And so there's this shuffling going on between main memory and disk, and that will slow everything up. But it doesn't slow things up by making them go more slowly. This is what Neil was talking about in terms of getting speed and speed being right. What it does happen is you get program latency, where the program seems to stop and then start and do something, and then stop and then start and do something. The program's running at its own speed, but there's these wee gaps, these latency gaps, while it's stopped, while it's waiting for something. Typically, it's waiting for a disk to come round, or it's waiting for something to get put onto a disk or come off of a disk. If your program has lots of startup sequences, fetching the registry, fetching the ini files, fetching the data, that'll slow things up, and if it's writing data. And the other thing that I've mentioned a dozen times, maybe 100 times to people, is that the thing everybody says, my computer takes a long time to start up. And the starting up slowly thing, 9 times out of 10, is to do with the fact that your computer is looking for a printer that you put in the landfill before coronavirus. If you install a printer and it goes to you set it up with a Wi-Fi and your machine's talking to it, and that's fine, but then you don't use the printer gums up, you get fed up with the printer, you put it in the bin. Nobody told your computer that. And when it wakes up, it still tries to see if it can send this stuff to that printer. And the printer's now long gone. I say it went in the landfill before the pandemic. But at startup, your computer will spend a minute, 2 minutes, continually trying to talk to network devices that it no longer has. So I recommend everybody have a look. And if you've got any old printers in the devices and printers panel, get rid of them, for the simple reason that it'll make your machine start quicker. So, for the purposes of this, I started and did a whole bunch of measurements in different hard disks. There's a couple of ways to do that. First of all, you can use the task manager. If you right-click on the task bar at the bottom of the screen, that'll bring up the task manager. And you can look at the disk tab on it, and it'll give you the read speed and the write speed, and it'll give you the resource manager, and the resource manager will give you a ton of information. If you're going to do that, though, you have to have files to transfer. You need to have 100 1K files or a gigabyte file or whatever to do the transfers back and forth, which means you have to have space for those files on both the disk you're coming from and the disk you're going to. You have to measure for both disks, because you can't move from one disk to another without both disks affecting the equation. You have to get rid of those files, either put them away somewhere safe or delete them once you're done. And then you have to worry about other things, like if you're using a network or you're using a USB or whatever. I will demonstrate that as we go through. And then once you've done that, you end up with sheets and sheets of numbers that you have to take averages of, divide by the number you first thought of, and throw one away to get some sort of result that makes sense. Alternately, you can get a program, and the one I use is called Crystal Diskmark. It's a wee, free, quick and simple program, and I'll put it up on the chat so that anyone that wants it can take it down and have a play with it. There's the task manager, and as you can see, there's the disk transfer rate. Initially, it's very, very high, up above 100 megabytes per second, but that's because it's using the caches. I'll talk about cache later on. And then it settles down to about 60 megabytes per second, and you can see me reading the read speed and write speed down there. And near the bottom of the task manager, you'll see a blue link to open the resource monitor. And if I open the resource monitor, it gives me much greater detail about what files are getting read and what the queue length is and how many items are in the queue and how many hits per second and all that good stuff. And I can do all those calculations to my own heart's content. Crystal Diskmark, on the other hand, opens like that. Across the top, there's the green all button. And when I press the green all button, it'll run all the tests. There's then the number 5 and a pull down. That's how many times I'm going to run the tests to get an average. The 1 gigabyte is the size of tests that I'm going to run. I'm going to run a gigabyte of tests for every test that I do. And then the drive that I'm doing, drive C in this case, has got 135 gigabytes out of 931 used. And I'm going to do all my calculations in megabytes per second. So I can pull them down to change the circumstances. There's also profile there. And if I pull down the profile menu, I can do it for optimum disk speed. I can do it for real world conditions. I can do it for maximum throughput. I can set up all these different profiles for the tests that I want to run. But I'm comparing apples with oranges all the way through these tests. So what I've done is I've used the default profile. And what I do is I use the default profile for all these tests anyway, because it gives me a really good indication of how fast or slow the disk is. The top couple of lines there tell me if it's sequential reads and writes, 1 megabyte files, a queue of 8 items in the queue and 1 thread doing the work. The next one's 1 megabyte sequential again, 1 thread, but only a 1 in the queue at a time. And then the bottom 2 are random 4K files, either a queue of 32 in 1 thread or a queue of 1 in 1 thread. Now the top 2 are equivalent to copying a DVD's worth or a video back and forth. So the machine's doing, that's the job it's doing, and there's nothing else happening. So it's a bulk transfer. The bottom 2 are more like when you're running JMRI or you're running Windows or compiling code where there's lots of files getting opened and closed at the same time. So the top 2 are bulk transfers, the bottom 2 are real world transfers. But let's get in among it. You've probably all seen one of these. This is the classic magnetic disk spinning RUSC. A miracle of control engineering. We used to talk a lot about that when we were teaching these things. If you scale up what's going on inside a 2.5-inch mechanical hard disk drive, then you've got an arm. And imagine an arm that went from the Clough Light at the tail of the bank all the way down to Girvan. And it was swinging from Girvan to the Aran Islands over in Ireland. And it was picking up cracks that are the width of a brick and 1/2 inch apart, because that's the sort of scale of the thing that it does. It is a brilliant, brilliant, brilliant piece of mechanical engineering to make it work at all, and to be able to manufacture them so that they all do that is also a brilliant, brilliant piece of engineering. And I'm utterly in awe of the people that do magnetic discs. We've also had 40 years of people optimizing these things to make them as quick as they can. And we have to know about the circle problem. How it works is you've got a magnetic coil, effectively, and a magnetic material, a magnetic surface. And it's Lenz's law, isn't it, that says that the voltage induced, or the magnetic field induced, is proportional to the speed that the two are running. But you've got a circular disc, and if you think about kids in a roundabout, the child on the outside of the roundabout is going much, much faster than the child at the centre of the roundabout. Similarly with this disc, the magnetic material out at the outside is travelling much, much faster relative to the head than the magnetic material close to the spindle of the disc, which means that when the disc's nearly full, the disc fills for the outside into the spindle. And when it's nearly full, the magnetic pickup and put down is happening at a slower speed, and so it's less reliable. So for that reason, most people leave about 20%, 25% of the disc. Once that disc is 160 gigabytes, once it's above 120 gigabytes of full, you're starting to think that disc is getting awful, awful full. If it goes up to the full capacity, you're liable to start losing data. And the last time you want to start losing data is when the disk's full. You don't mind losing it when you've got hardly anything on there. You can fix it, you can throw it out and put a new one in. But if you've got all that stuff on it, that's the last time you want it going bad on you. So you always have to worry about that circle problem. Discs used to come in these three speeds: 5400, 7200, and 10,000 RPM. I've had a wee look round about in the past week. You don't see them anymore. They're nearly all 5400 RPM because they're not really getting used. Nobody's trying to squeeze the maximum performance out of a mechanical disc anymore. They're using, if you want performance, you move up to an SSD of some description. So for that reason, the ones that you can now buy tend to be 5400. Cache. These discs have cache memory on them. And if you're buying one of these discs, then that's the first thing you look at. Has it got 1 meg, 2 meg, 4 meg, 8 meg, or 16 meg of cache memory? What cache memory is when you ask that disc for information, and let's say you want track 100 sector 12, the controller on there will go to track 100 sector 12 and lift the information to start and pass back to you. But while it's there, it'll pick up sectors 13, 14, 15, 16, 17, 18, 19, as much as it can, because if you've just had sector 12, the thing you're most likely to want next is sector 13. And if it's got that in its memory, it can just hand it to you without waiting for the disk to come around again. And so by using cache memory like that, the disk can appear to be a lot quicker than the actual mechanical spinning thing is. The ultimate expression of this was a few years ago, Seagate and one or two others started making hybrid disks, a 750 gigabyte mechanical disk with a 32 gigabyte SSD built into it. And what that would do was all the stuff that you were using the most often, like your Windows directory and your My Documents directory, would all be on the SSD. It was only a tiny SSD, but most of the time, the disk could get stuff straight from the SSD portion. And so these disks seem to go like the clappers compared to an ordinary mechanical disk. I don't know if you can still get them. I've got some lying about, but I don't use them anymore. But if you were looking for a fast mechanical hard disk, then that's probably the state of the art. There's the speeds for magnetic disks that you get from Crystal Diskmark. Over to the left is the disk plugged directly onto the SATA cable inside the computer, the way you're supposed to fit an SSD. But if you look at the middle one, that's the same disk. If you look at the D drive, 932 gigabytes, that's the same magnetic disk plugged onto a USB 3 enclosure. One of these USB things that sits outside your computer and you can use it for external hard disk. And if you look, it's the same speed. The mechanical disk there is the factor, it's the telling factor. USB 3 is much, much quicker than a mechanical hard disk is. And so putting it on a USB enclosure doesn't make any difference unless it's a USB 2 enclosure. If you look at the USB 2 enclosure over to the right-hand side, you see that a USB 2 enclosure slows everything down. Maybe not so much for the thrashing, all the little files, but certainly if you're trying to do bulk transfers, a USB 2 enclosure is bad news. If you want to buy one, what I have done is for each of the discs that I'm putting up, I've put an example and then I've went to Amazon and I've said, I would like a 1 terabyte example of this. 1 terabyte's the sort of size that you would be buying right now. It's more than enough for any kind of PC that we're likely to be using. It's big enough to run practically anything. And it's the low end of terms of having to buy one of these things. So pay 30 quid a terabyte for mechanical drives at the minute. And I looked these things up on Wednesday or Thursday of this week. So that's fairly recent information. Mechanical drives are being replaced more or less by SSDs. An SSD is the same width and the same length and the same thickness and the same connectors in the same place and the same screw holes. Everything's identical to the mechanical hard disk, which means all you need is a screwdriver. And you can open the box, take the old hard disk out, put the new hard disk in. It is literally a drop-in replacement, except for it's a lot quicker, a real lot quicker. Initially, these things had current issues. I remember at a meeting up in the Scout Hall discussing this with a fellow IT manager. I'd been putting a whole load of SSDs into my server room, and it turned out that my electricity bill doubled, because the SSDs were taking a lot more current than the mechanical equivalents. But that was a decade ago and it's now sorted. The SSDs now draw a lot less current than the mechanical drives. There was always a promise that they would take less, but they've only really achieved that in the last 5 or 6 years. Because there's no moving parts, there's higher reliability, and so it should last longer. However, there's memory wear. If you read and write to the same sector of a solid state disk, then that solid state disk will eventually start throwing errors. So to stop that happening, the controller on an SSD will do what's called wear leveling. If you copy a file off and change it and put it back, it won't write it over the same segment like a mechanical disk would. Mechanical disk does that to keep things away from the spindle for reliability reasons. The SSD writes it somewhere else so that all the memory is getting used equal amounts of times for reliability reasons. So as a result, if you ever have to read the raw data off one of these to try and rescue one of these that's been corrupted, and you try to rescue files off it, it's a real pain because every file's on it 16 times and you're trying to find which one's the one that counts and so on. And because of the wear leveling, the controller will mark, it keeps a table of sectors that it can't use anymore because they've got errors on them. And so you end up with this big table of bad sectors. And that means that as the disk gets full, as it gets to about 80% full, you're getting into the area where you're going to run into the wear leveling issue. And so you never let an SSD get above about 80% full either. For an entirely different reason to why you don't let the mechanical one get more than about 80% full, but you keep the same rule applies. When you get to about 80%, it's full, time you had a new disk. And that's fine. These are all, by the way, NAND memory. If you buy a PIC chip or a flash EEPROM, an electronic chip to put on a board, or the memory that's inside the PIC chip for storing settings, that's what's called NOR memory. and it's much slower, and it's much slower to access and slower to read back, but it has different reliability characteristics and so on. These are all NAND memory, and if you ever see one that's not NAND memory, you probably want to give it the sniff test. Bits per cell, I'm not going to talk about. As these things go on, the number of bits per cell gets higher and higher, and it means that you can get bigger and bigger disks. Here's the speed test. If I connect it direct to the SATA, it's quicker than the USB. Remember the mechanical drive? Direct to the SATA was about the same speed as the USB. We're now seeing the limit of the SATA connector. That left-hand panel shows me how fast a SATA connector on my little Lenovo can go. The USB 3 enclosure is again very, very similar to putting a mechanical drive in there. We've reached the peak of what USB 3 can do there at 450 megabytes per second at the top. Is about as fast as you'll ever get out of USB 3. And a USB 2, again, relatively poor by comparison. That doesn't mean that you can't use a USB 2. It will work, but you might find you get a wee bit disappointed by the amount of data throughput that you get on it. Here's a very typical drive. And again, I went to Amazon and I searched for that. And look, lo and behold, I've bought this a couple of times. I use these quite a bit. That's a 1 terabyte Samsung, 50 quid. 50 quid per terabyte as opposed to 30 quid per terabyte for the mechanical, the slower drive. And how much slower? There's the mechanical ones from earlier compared to the solid state ones from now. The mechanical one, the USB enclosure, doesn't make a difference unless you're USB 2. The solid state one, you actually see the limits of the SATA, and the USB enclosure, you're starting to see the limits of the USB enclosure as well. While we're talking about these things, there's an SD card. Now, an SD card is actually an SPI controller with NOR memory. Remember I talked about NOR memory being slower. So you've got NOR memory and an SPI interface that will only run at 100 kilohertz or 500 kilohertz if you're lucky. And then it's hanging off a USB 2 interface. If you actually go and chase, if you've got a laptop and it's got an SPI socket on the side of it, and you go into the device manager and you chase the connections to that SPI card, it'll go via one of the USB 2 connectors. And that's why the performance is so meh. It's not, you're never going to get any performance out of an SD card. And it doesn't matter if you get a times 10 or a times 20 or a times 200 SD card. The very fact that it's an SD card means that you're not going to get much speed compared to a hard disk. There's a USB 2 and a USB 3 thumb drive, again for comparison. I take it that everybody knows that how you tell it's USB 3 is it's got a blue tongue. If you notice, that thumb drive has got blue sticking out the end of it, the tongue of the USB, and that's the USB thumb drive, the USB 3 cable, and the USB 3 connector on your laptop or computer. I've always got that blue plastic tongue. So if it's a blue plastic tongue, it's USB 3. If it's not blue plastic tongue, it's probably black plastic and it's USB 2. If you get it from China, they sometimes put blue plastic on USB 2s to try and get you to buy them. Let the buyer beware. Now, before I do the next wee bit, I've got to talk about PCIe or PCI Express, PC interface. Back when I was a lad and PCs were a new thing, they all had this industry standard architecture for expansion cards on it, ISA cards. And then they became 16-bit ISA cards. And then they became 32-bit EISA cards, and then they became PCI cards, and then they became something else and something else and something else. And those days are in the past. They're long gone. Nowadays, every expansion card on a PC that you buy is something called PCIe. And they're all the same, even though they're sometimes different. Right, I'm going to nip onto the next picture and come back. There's a handful of PCI sockets. These are actually from the Radio Spares and Farnell catalogues and places like that for buying the sockets for repairing computers. But you'll notice that to the left of every one of those sockets is a little area of 22 pins. And then there's a key, and then there's the rest of the socket. And the rest of the socket is of variable length. There's one of them there that's got less than 22 pins. And there's one there that's got about 180 pins. Right? Those are all PCIe sockets. And that's what's inside a modern computer. The bit to the left with the 22 pins contains the power, the interrupts, the chip selects, the clocks, all those housekeeping, controlling sort of parts of the interface. That's what those 22 pins are. And then the bit to the right is one or more PCIe lanes. Basically, the more lanes you've got, the more bandwidth you've got. The more bandwidth you've got, the more data you can transfer at the same time. So the one at the top left there's only got one PCIe lane on it. So that'd be useful for a modem or a printer or a joystick that doesn't input or output much data. Whereas the one at the bottom right is a 16-lane PCIe. If you see it on the motherboard specs, it'll say PCIe X16. And that means it's got 16 lanes. And that'll run a GPU or a fast video card, because it's got all that bandwidth to transfer all that information at the same time. So if I go back to my previous slide, you've got that common connection on the outboard edge. You've got a number of lanes, which makes the socket longer. The more lanes you use, the faster your throughput, the quicker everything works. For networks or Wi-Fi, an X1 or an X2, a short socket will do fine. If you're wanting a video card or a GPU, you need an X8 or an X16 socket. However, if you open up your computer and you've got an X4 PCIe card and you've got a big long socket, you can plug it in, it'll work. The power and the clocks and all that good stuff on the little bit will make the board work. It'll just not have the bandwidth that that socket, you're wasting half the bandwidth in that socket, but you can plug a shorter socket into a bigger connector. You obviously can't connect a big long socket into a short connector because it won't physically go. That said, you can actually buy PCIe SSDs. There's two of Intel's standard 1.2 terabyte SSDs. These are what's called the 750 series. The one on the right is a SATA, and the one on the left is a 4-channel PCIe, a 4-lane PCIe. And the one on the left is a wee bit quicker than the one on the right because the mSATA limits the speed of the thing. This was no good for people making laptops. And in the past 10 years, it's been all laptops and tablets and also all-in-one computers. And the components in an all-in-one computer are essentially laptop components. So it's laptop disks, laptop RAM, laptop everything. And so they needed a smaller standard than these PCIe sockets. So they come up with mini PCIe, and at the same time, they also came up with mSATA. And unfortunately, they put them on the same shape of connector, which is a small sideways version of the PCIe socket. Originally, they put these things in to let them attach Wi-Fi cards and network cards and stuff like that. But then they noticed that the SSDs were getting too big. The 2.5-inch SSDs that I showed you earlier were too big for modern slim laptops. And so they started putting a tiny version. There it's there. And that's an mSATA drive. And that mSATA drive will fit in an mSATA socket. But over to the right, that's a mini PCIe. And that one's an Atheros. It's a pair of radios. If you look at the top of that wee card, you'll see it says channel 0 and channel 1, and there's two tiny coaxial connectors. One of them's for Wi-Fi and the other one's for Bluetooth. So that one there is a pair of radios, but the one on the left's a hard disk. And the thing about these is the sockets are the same, but they won't plug into each other's. If I plug the radios in where the hard disk should go, it won't work. If I plug the hard disk in where the radios should go, it won't work. So you can't get these wrong. Luckily, they're being phased out. They're not as popular as they were, which is good news because it's a source of confusion. But you may open my laptop, you may open my computer and find these, and you really have to know about them. Here's a Lenovo laptop with the back off, and it's got both of these. Up at the top, you see the hard disk, and the hard disk is on one of these M2 sockets. And down at the bottom, you see the radios. And the two wee coax connectors this time have got two wee coax plugs in them and two wee coaxial cables heading off in the general direction of the screen. What they do in a laptop is the aerials for the Wi-Fi and the Bluetooth are on the screen, so that when you lift the screen up, the aerials get as much height as they can, because a little bit of height gives them a little bit of extra range. And so the aerials are on the screen, and then there's little coaxial cables go back to the cards. So this was a mess and it needed fixing. And the way to fix it was something called the next generation form factor. NGFF, next generation form factor. First of all, the SATA limit. When we got to the SATA drives, we actually got to the SATA limit, whereby the SATA interface was slowing down the SSD. And there had to be a way past that. So the drive that I just showed you is a SATA, it's a micro SATA. The NGFF doesn't use the SATA limit. It connects straight to the PCI bus. So it's back to how many lanes can you have? How much memory bandwidth can you have? And these things were so successful on laptops that they now use them on desktops as well. So you can now buy a desktop motherboard and it's got a socket on it for putting one of these NVMe drives in. You may even find, if you've got a computer that you've bought in the last 4 or 5 years, that it's got a socket for one of these fast drives on it. It'll either be an M2 SATA or one of these NVMEs. And you have to get the keying right. I'm going to talk about keying with these things a lot because it's very easy to make mistakes with this. The other thing is the Lenovo desktop computers that I use are 10 years old, and I can put NVMEs into them. I'll show you how I do that in a minute. But if I do, I can't make it boot from the fast drive because the BIOS doesn't recognize NGFFF disks as being bootable hard disks. So in order to do that, I have to go to the manufacturer and install a BIOS update. Now, not everybody's comfortable with BIOS updates. You can, if you're really unlucky, create a machine with one, but it's very, very rare that it happens. And if it does happen, give me a shout and I'll help you to fix it. And did I mention keying? I've got to mention keying. Keying is really, really, really important. There's two of these NGFF disks over to the left. And if you look at the connectors, they've got a little slot where the key on the socket goes. And it looks like you could just turn it over and make it fit. It doesn't work that way. The mSATA is a completely different shape of plug. That'll not work in anything except an mSATA connector. But the mSATA connector is not to be confused with the micro PCIe for putting the radios in. So you've got to get that right as well. But the mSATAs, I'm talking about them because they still exist, but they're going away. So don't worry about them so much. NGFF comes in half a dozen different lengths. They're always 22 millimeters across, and they can be 30, 42, 60, 80, or 110 millimeters long. And notice the connector is at one end with the keying on it. I'm talking about the keying because the keying is important. And at the opposite end, there's a notch for attaching it to the board. That notch will become important in a minute. There's this keying thing. There are 3 or 4 different keying possibilities. B key and M key are far and away the most common, the most popular. The B key has got 6 contacts at one side of the socket, and then a wee notch, and then the rest of the pins. And M key has got 5 contacts at one side of the socket, and then a wee keyway, and then the rest of the pins. But they're not compatible. It looks like you can just take a B key and turn it over and plug it into an M key socket. But it doesn't work that way because there's 6 connectors in one and 5 connectors in the other. So these things you have to get right. The one at the bottom there is a B and M key. You get that from a big cheap warehouse round at the local retail park. B&M's? No, you don't. That's a version of it that's designed to fit either one. And that you'd think that would be the natural thing to do, put the 2 keyways in. But obviously, if you put the 2 keyways in, you get rid of some of the non-power connectors, because you have to have power connectors at both ends. And so you've effectively half the width of the normal connectors. And so you don't get as many lanes. And so you don't get as much bandwidth. And so the B&M connected one will be slower than one of its either a B key or an M key. They've got more bandwidth because they've got more channels. They've got more lanes in the PCI connector. Now, looking at a modern motherboard, literally I was lucky to stumble across this because all the important stuff's in orange. If you look to the right, you see the 2 sockets for putting the memory, the RAM, for the motherboard in. And just in front of them, closer to the front of the motherboard, you see an orange socket for the master mSATA. That's the fastest of the mSATA channels, and that's the one that will boot automatically when you switch the machine on. So that's the one that you plug your boot drive into, the one with a different coloured connector. And then to the left-hand side of the board, you see 2 PCIe connectors. There's a little short one. See a PCIe, a single lane one. That's for connecting a Wi-Fi board or a network or a printer, a parallel printer, something like that that's slow, would happily go into that little PCIe ×1 socket, which is very, very close to the left-hand edge of the board. And then there's a big, long, orange PCIe ×16 socket. And that would take a fast graphics card or a GPU if you wanted to make a number crunching computer or whatever. Next to that, you'll notice an NGFF socket on the motherboard. You see the M-keyed socket up at the top, and then further down the board, there's space left, except for the 3 bosses sticking up to put the screw into, depending on the length of the card. It's got that notch at the top for a screw to hold it to the motherboard. When you plug this thing in, it sits at 45 degrees when you push it all the way in. And then you have to push it down so that all the connections are pressed in. And to hold it in position, you put a wee screw onto one of these things. And there's an NVMe on the motherboard. And look at the speed of that compared to the SATA. Particularly for the running lots and lots of little disks, lots and lots of little files. It goes like the clappers, which is why a lot of people are going towards them. If I put mSATA on a laptop, then you see that because it's an mSATA drive, you get the mSATA limits exactly the same as if it was the big mSATA SSD that you can buy to replace the mechanical hard drive. And also, while I was at it, I took one of those 870 Samsungs and encrypted it. Some people have to encrypt stuff for reasons of it's got medical records or financial records or confidential records on it, and you have to run your drive encrypted. If you encrypt the drive, it kills the performance, stone dead, because every byte that goes on or off it has to get sent off into the encryption engine, and that takes time. And so the encryption murders the performance of the drive. mSATA is going away. Because mSATA is going away, mSATA is becoming rarer. You're less likely to encounter mSATA. And because you're less likely to encounter it, it's getting more expensive. £70 per terabyte to buy one of these. Bad luck if you happen to have a laptop that's got an mSATA socket on it and you want to buy a replacement drive, because you're kind of stuck for options there, and the options are getting more expensive as time goes on. The other side of the same coin is that the NVMEs are getting cheaper. They're down to below £40 per terabyte. So NVMe is looking like a good option if you were wanting to upgrade your machine. The performance is scintillating and the price is getting better and better and better. If you want to do it in an external enclosure, you can buy one from our friends in the East for about £14 or £15. These things are as cheap as chips. They're made of plastic, and the first time you try to open it, you'll probably break it. So when you do get it delivered to you, very, very gently open it, because if you push it too hard, it'll break to bits. They're not robust things. They do work, but the limit, there's an NVMe, and I've got it on a USB-C connector. And again, the USB-C is the limiting factor. It's going as fast as USB-C will let it go, which is USB-C speeds, even though it's an NVMe. But the benefit of that is it's out on my desk. So I don't need to open the box to put it in there. And it's, relatively quick. It's as quick as anything else. But the USB-C is the limiting factor. And again, an M2 SATA in a USB 3 enclosure, the limit again is USB 3. So if you're going to use an external enclosure, it's not worth buying anything other than a USB 3, and you're not going to get any great performance above that out of a USB 3 or a USB-C. Now you can buy these for a tenner, and I put two up specifically to let you see the difference. The one on the right, you can see the 22 pins with the clocks and the power supplies, and then you can see there's about 6 pins after that, after the keyway. That's a 1-lane NVMe drive. And that 1-lane NVMe drive is going to have a 1/16 of the performance of the one at the other side of the page, which costs the same amount, and is a 16-lane drive. If you get a 16-lane drive, it'll fly with the birds. If you get a 1-lane drive, you get 1 lane, and you're going to be limited by the 1 lane. How limited? There's the limits there. That there is a 256 gigabyte NVMe on a 4-lane drive. If I put it on an 8-lane or a 16-lane drive, it'll be quicker. But on my 4-lane drive, a 4-lane PCI card, there's the speeds out of it. And there's the same drive, the same NVMe on an external enclosure. As I said, on the external enclosure, USB tends to be your limiting factor. So if you're going to buy an NVMe to plug into your machine, see if you can't get one of these PCIe cards for a tenner. It'll make things so much quicker for you. Lastly, there's RAM disk. You have to install a load of RAM in your machine, obviously, because it uses the RAM of the machine as a disk, and you have to buy a program. You then, once your machine's up and running, you copy the stuff over to the RAM disk, and the RAM disk appears like a hard disk. A very, very fast hard disk. And it's lost when you switch off. If you press the reset button or you switch the machine off at the mains, everything's lost for the RAM disk. All the rest of these, obviously, are hard disks. You switch them off, you switch the machine back on, everything's the way it was. Not so the RAM disk. It's only for if you want something that uses a disk, but it needs a really, really quick disk. The software costs you about a tenner. The memory costs you an arm and a leg, because you've got to put 32 gig or 64 gig of main memory into your computer, and that's going to cost money. However, the performance is enormous. That's RAM disk on my machine upstairs. As you can see, I get 100 times the performance that I get out of any SSD. I only use it for things that involve hashing databases or hashing thousands of files, where I'm going to be, doing something that's going to take all night. This will take it down to doing it in half an hour because it's so much quicker. So, in summary, mechanical hard disk, we all know about, £30 a terabyte. It's not quick, but it's adequate. We've been using them for decades, so we all know about them. They're tried and tested. Typical SSD is about £50 a terabyte, typically 5 times faster than its mechanical cousin. If you're using it the way we use it, which is turning the computer on for 2 or 3 hours a day and not using it that hard, it'll last longer than any of us will. If you put it in a server and thrash it 24 hours a day, 7 days a week, you'll have to replace it in 4 or 5 years. But for light use, more than adequate. It's a cheap and very simple drop-in replacement or upgrade. You don't need anything more than the sense you were born with and a small screwdriver. NVMe is £40 a terabyte, and I recommend you spend a tenner on that PCI card. You need to have the appropriate slots, either on your laptop or on your desktop or on the PCIe card you buy. It's faster than an SSD, depending on the number of lanes. Hopefully, as I say, by the end of today, if nothing else, you now understand these PCIe lanes and what memory bandwidth is when it comes to writing to disks. Keying, did I mention keying already? B keys and M keys, you have to get that right. I recommend you buy the enclosure of the PCI card first and read it and count the number of connectors to make sure you then buy the drive to fit it. Because the number of times I've seen people had to buy both because they bought the wrong one, and you end up having to buy the same thing twice. Lastly, RAM drive goes like stuff off a shoe, but it's dear, very, very fast, but it's a wee bit specialist. And that's me done. Any questions? Are we getting that stunned silence that happens at this point?